is a wave? Well, the first thing that I think about is a sine wave. When I think about waves in general, because a sine wave, or like, we're not gonna get into like superpositions of waves. Like, if you just think about like a simple wave that has a wavelength and a period and all that stuff, a sine wave can describe any kind of wave. If
in essence,
there are more complicated waves, but those are just, you're just adding sine waves on top of sine waves to make those more complicated waves. But if we're talking about like waves in the water, sine wave, all that
all
stuff.
of them can be, because now what we're basically talking about is extrapolating the mathematics behind what we have as the physics. Or not the physics, but like the real world. So we're seeing something, and especially with physics, we have this handy thing called, or not called, but basically just equations of motion. And with all waves, there's an associated wave equation. And this is simply a fundamental property of any wave. And if it's a sine wave, it's literally just sine x, right? Because that's the wave. So the whole point of this is using the mathematics behind all, behind sine, behind trigonometry. We can apply these to the real world and extrapolate data about them through these waves. So what you were talking about a second ago is something that we also did speak about in a history of physics episode, a Fourier transform, or like a Fourier.
Not transform.
Well, not a
Fourier
transform.
series.
Fourier series is basically what you described by adding up the different separate sine waves, because cosine waves are basically sine waves. So you're basically just adding multiple sine waves, and you just get a very complicated wave. You can shift some of them and you can get something else.
Did you know I recently actually really understood for the first time what a Fourier transform was?
Because of quantum mechanics?
And it's not because, well, technically I should have. There were notes that I didn't read them though. But no, I'm talking about maybe during the summer, I looked up Fourier transforms, and I actually understood what it was. Very interesting. If you're in or let's say going into university math, maybe let's not say first year, that's a little bit too complicated, but if you like to look ahead, I definitely recommend looking at Fourier series and then Fourier transforms. Very interesting.
Very interesting. Fourier, and they are, again, the building blocks to how we get our waves. Because if you think about it, now waves can be so many things. Like, we think about them as light waves, sound waves, but there are so many different types of just waves when you're talking about it in general. We just have said, okay, like these commonalities are what we see. So even when we extrapolate this using Fourier series and stuff like that to make a more complicated wave, all that's really doing is just, again, getting us a better understanding of the properties of that wave. How does this wave move? Number one, with position. Number two, with time. That will be your two-dimensional wave, right? So there are a lot of advantages to using all of these extra principles just to get a better understanding of our wave, right? And every wave, just fundamentally speaking, a physical wave at least that we see in nature, all of them have two separate fields. All of them have two separate fields that is basically oscillating back and forth. Now, the whole thing about a wave, why is it really called a wave, is because the idea is that, well, it's waving back and forth from a point of, I don't want to use, an equilibrium point, right? So there is some middle ground, and the wave, or most would just oscillate back and forth between them.
But what do you mean by two mediums, like you said?
Everything requires two mediums. Now, the fundamental light will require electro and magnetism, right?
Okay.
And they require two fields to propagate. The same way with sound, it requires strain and stress, which are two different properties of the air that basically allow sound to propagate through it. And all other physical waves that we see in, nature, anything real, again, mathematical is obviously different. I'm saying anything physical that we can actually see in the real world, sound, light, obviously the biggest ones, you can assign these fields to it. So in more complicated and more advanced, mathematics and field equations and physics, we can actually maybe deduce these fields, part of all of these equations, and actually understand not only how the space around it is moving, but how the individual fields are moving.
Oh,
right. And that's an advantage of this relationship between these two fields that have to be present for a physical wave to occur. Right. And because both of them are basically pushing back and forth, is how the wave is able to propagate. And this is true with electromagnetism and also through sound. Right.
But I don't actually know if this 100, like for 100% certainty.
Let's say
I'm saying like the electromagnetic fields that oscillate, they don't like push and pull each other. You know what I mean?
They're
like
perpendicular.
they're oscillating
perpendicular.
perpendicularly.
They're perpendicular, but they require. What I'm trying to say is, for the wave to exist, there is a requirement of two fields. Is what a requirement is for a wave to exist.
All right.
Right. And these two fields basically or allow it to propagate through space-time. Right. In any situation, in sound waves, we can talk about, it would still be space-time, but you know what I mean? Like it would be probably air and stuff, because that requires a medium to propagate.